Hello and welcome to Microsoft Hates Greg. My name is Greg Deckler, and today we're going to be taking a look at anomaly detection using only DAX. Now you might be saying, why, Greg? Why are you doing this? Well, we'll get to that in a minute. We don't do things just because they're practical or anything else. We just do things because we want to do them on this channel. Okay, so anomaly detection in DAX. So the first, I don't know where I came up with this idea of doing anomaly detection in DAX, but somehow it came to me, and I decided, let's try it. So first thing I had to do was go out and figure out, okay, what are some anomaly detection algorithms that are out there? So I found this article, Towards Data Science, which is a great website I've used in the past for some of this type of statistical stuff. And this Satyam Kumar, hope I pronounced that right. It goes through and talks about what are anomalies, how to detect them, and then goes through these different algorithms, isolation forest, right, and then local outlier factor, robust covariance, and then some SVM algorithms, which, if I remember my data science and machine learning correctly, is a scalable vector machine. So I took a quick look at each one of these, and I decided upon local outlier factor as the one that, at least at first glance, was probably the most reasonable to be able to implement in DAX. Which, in case if I was correct, and it is the most reasonable, oh boy, those other ones must be crazy. All right, so we can go out, with another first step, second step, we can go out to Wikipedia and we can look up local outlier factor, and basically kind of get a basic idea behind, what the how the algorithm works, and then, and then it goes through and provides some examples and some graphics and things like that, some formulas. But Wikipedia is, it's mostly about kind of theory and that about sort of stuff like that. It doesn't really provide practical examples, which is problematic when you're trying to recreate this stuff and figure it out. So third, I went through and I found some articles on somewhere that had some actual examples and walked through the calculations and, step by step. So the first one I found was, again, Towards Data Science, Local Outlier Factor. I'm not even going to try it. But this article goes through and, introduces some of the concepts that are explains them very well. But most importantly, right, provides an example. So A00, B10, C11, D03, find the outlier, which obviously we can look at this and say it's going to be D. But how do we get there mathematically? And then this K equals 2, I'll get to that. That's K. So you're trying to, so one of the things you have to pick is your K value when you're doing this. This in case means your Kth nearest neighbor. So the Kth nearest neighbor to A is C in this case, because it's the second closest. So if your K equals 2, C is your second closest nearest neighbor. Anyway, we'll get into all that. I found another example by do.dev on Medium that doesn't explain the concepts as well, but maybe it does a little bit better job of the example in terms of, it kind of gives you, here's what we're going to go through, and then introduces the problem, goes through each of the calculations, and it agrees 100% with this article in terms of the results for the LOF measure definition or measure values and things like that. And I found a third example. This was on, well, I'll get to this in a second, which goes through the same exact example, and it all agrees up until the point of the actual LOF calculations. And I think it's an error in the mathematics. I really do, because, for example, they start out with the same thing that's on Wikipedia, which is this formula right here. And if you look at Wikipedia and you come down to this LOFA, right? So this part right here is equivalent to this part. But then they say that this is equal to the sum of this versus the sum of the reach distance, which is not what Wikipedia says. It's saying that those are not the same formulas, and they come out with wildly different, and then they do identify the outlier, which is point D, but they get completely different numbers for these LOF numbers that they have. So, and I don't know, this just doesn't seem right to me. But maybe I'm wrong. Maybe this is the right way to do it, and these two other examples are wrong. But if you if you got your degree from the Department of Computer Science and Engineering at the Hong Kong University of Science and Technology, I don't know, maybe your degree is kind of garbage. I don't know. somebody that knows way more about this stuff can come and tell me I'm wrong on that. But so I based mine around these two examples, which came out and they agreed with one another. Maybe they're both doing it wrong, but it seems to also fall in line more with the Wikipedia calculation here. All right, so let's get into it. Now I started with an enter data query, right, where I just entered my data, these three columns, A, B, C, D, 0, 0, 1, 0, 1, 1, and 0, 3. All right, so let's close that, get that out of the way. And now this is the end result. Okay, so I've got a scatter plot image here, or visual here. This is the table with the LOF measures, the actual results. In this one, I have the LOF measure is controlling the size as well as the color. So I've got a gradient conditional color formatting on, and so the most non-anomalous are gray, and then it starts going to red the more anomalous that it is. Okay, and and this is the measure right here. So there you go. Very easy kind of measure to go through. I'm not going to try to explain it in terms of this measure. What I'm going to do is I'm going to explain it in terms of the way I actually created this thing originally, which was using some tables and some calculated columns, some calculated tables and columns to go through, and that's how I originally developed it, so I could kind of step through each part of the process, make sure it was getting the same answers as the examples, and then away you go. At the end, then I just created this LOF measure and just combined all of that code into a single measure. All right, so let's get into it. First step in the process is we need to, and maybe this one's the best one to do. So first thing we need to do is okay, there's the problem. We need to do the distance calculation. So we need to find all of our points, A, B, AC, AD, BC, BD, CD, and find the distances between them. And in this case, we're using what's called the Manhattan distance. So Manhattan distance, so instead of using like the Pythagorean theorem, we have x and y points, and a squared plus b squared equals c squared, and we can find the hypotenuse. What we're doing is we're using what's called Manhattan distance, or at least these examples use that. So I use that in mine, which is basically you take the absolute value of the difference between your x coordinates, right? And then you add that to the absolute value of the difference between your y coordinates, and that together equals your Manhattan distance. Okay, that's Manhattan distance. All right, so first thing we needed is a table of all of our points that we're interested in. This may seem a little bit crazy just to get and then what this table returns is just ID1 and ID2 columns. This is a calculated column we'll get to. So the first step in this, I'll just zoom in here. First thing we do is we select, our ID column out of our original table, and we call it ID1. Then we do the same thing, but we call it ID2, and we do a generate. So we generate the Cartesian product between the two. And then we're not interested in points like AA, BB, CC, DD. So if the ID1 and ID2 equal one another, we're going to filter those out. So that's what the first table does. Now the second table is it's kind of a little bit tricky, but so think about it in terms of you're going to, if you're generating a Cartesian product, you're going to end up with rows that are AB as well as a row that's BA. Well, we only want one of those really in our calculation or in our table, minimize the calculations that are involved. So what this table does is basically creates an ID3 column. If ID1 is less than ID2, then we return ID1. Otherwise, we return ID2. And same thing for ID4 is the reverse. If ID1 is greater than ID2, then we return ID1. Otherwise, we return ID2. So this, at the end of the result of this, is that we have, our table. If we have an AB and then AB and a BA, now we end up with an AB. And so now we can just select the columns. We can call it ID1, ID2, select ID3 and ID4, and then do it distinct across that. And now we only have the pairs of points that we actually care about. AB, AC, AD, BC, BD, and CD. Okay, so that was that. So the next piece is that we need to calculate the Manhattan distance. So that's pretty simple. We grab our ID1, grab our ID2. We do our X1 is we just go look up our value right in our original table, where the ID is equal to ID1, grab the X component. Same thing for Y, same thing for ID2. And then we can, there you can see there's the Manhattan distance is the absolute difference between x1 and x2 plus the absolute difference between x1 and y2. And we come back with our table, and it's 1, 2, 3, 1, 4, 3, which should agree with our 1, 2, 3, 1, 4, 3. Yep. So we get the same answer. Okay, so now we need to find the kth nearest neighbor distance calculation. Okay, so basically, again, like as I was talking about k equals 2, we want to find the second nearest neighbor for each point. And we want to know what the distance is to that point. So we go back to our original table, and I've got this KMD calculated column here. So now what this does is we can do we grab our ID, we go look up in we filter our table 2 where the ID is equal to the ID, ID1 is equal to ID, or ID2 is equal to ID, because we don't know which column it's going to be in technically. And then what we do is we grab our top. Now this K right here, this is actually a measure. I could have hard coded it to 2. It's the only place that it's really used. I will say, generally, it's a really bad idea to use a measure in a calculated column, with the exception being if that measure is just a constant value. So that'd be the one exception where I'd say it's okay to use a measure in a calculated column, because it's always a constant. Otherwise, you're probably going to get yourself into trouble because measures are dynamic based upon what you're doing in Power BI and the interface, versus calculated columns are not dynamic. They're calculated time of data refresh. So this is the one exception. So basically, I grabbed the top 2 from my table for that have my MD, right, my calculated column there in ascending, and then I grab the max value of MD for that, and that gives me my value to my second nearest neighbor, which comes out to be 2, 1, 2, 1 for A, B, C, or sorry, 2, 1, 2, 3 for A, B, C, and D, right? Which again should 2, 1, 2, 3. There it is. So we got that correct. So far so good. Okay. So that's our KMD. That's our second nearest neighbor in this case, to each of the points, and the distance to that. Okay, so now we have to find out how many points are within the same distance as the kth nearest neighbor. Okay, and in that case, that is this K neighborhood. So we grab our K-MD value, we grab our ID, we do a filter of our, okay, before I get to that, so this seems kind of naughty to me. So I fully expected when I was doing this was to run into a circular reference, because table 2 is calculated based upon table 1. But now I'm using table 2, which is calculated from table 1 to calculate a column in table 1 that really is coming from table 2, which is based upon table 1. And that seems very circular to me. I fully expected a circular reference error in doing this, but somehow I didn't. So I don't know. I've got some thoughts around that, and it's like, oh, have we found a way to do recursion in DAX somehow? I doubt it, because I've tried for years and years to do it. But anyway, so this seems kind of naughty to me, that we shouldn't be allowed to do this, but we are. So bonus. All right, so on to K neighborhood. I need to find out how many points are within. So if my kth nearest neighbor is 2 away, I want to find all the points that are within a radius of 2 away in terms of the Manhattan distance. So I grab my KMD, I grab my ID, I filter my table 2 where my ID equals my ID, or ID2 equals ID, ID1 or ID2. And then I count rows where I filter that table where the Manhattan distance is less than my KMD. And for each of these, I come back with 2, which again agrees right here, all of them too. So this means that there's 2 points for each of the points. There's 2 points that are within the Manhattan distance of the second nearest neighbor. That's what that means. Okay, local reachability density. So this, it gets a little bit wacky. Let's go ahead and take a look at it. This was probably the hardest part for me to implement and understand how the algorithm is supposed to work. So what I do is, so what I'm trying to do, it's just, well, I'm not going to try to explain it. There's a formula for it, right? And that's this formula right here. But you have to get the right numbers plugged in everywhere. And if you want to know more about this formula, it's that some blah blah blah. You can look it up on Wikipedia and that. But it's just a it's just a metric that we're calculating, and it's called the local reachability density. So I grab my KMD. I need that. I need my K neighborhood, which is the number of points in my neighborhood, right? And then I grab my ID. I do the same thing where I filter the table to where ID equals ID, or ID1 equals ID, or ID2 equals ID, and the Manhattan distance is less than my KMD, the distance to my second nearest neighbor, right? Now here's the interesting part. According to the algorithm, um, the way that it's supposed to work is that what you want to plug into the formula for summing across this is the maximum value between either the point and the point that you're interested in, or the point and the points that you're interested in second nearest neighbors KMD. I'm probably not explaining that very well, but you want that max distance. So it's either going to be the distance between the 2 points that you're interested in, or it's going to be the distance between that second point that you're talking about and its second nearest neighbor. Whatever, which one, if that distance is more than this distance, then you want this value. Otherwise, yeah. Anyway, that's the way the algorithm works, apparently. So that's what this little thing here is. I'm taking my table that I have and I do a max MD column. I go and look up value. If ID1 equals ID, then if ID1 equals ID, okay. So if ID1 equals ID, then it's ID2, right? That's the point I'm interested in. Otherwise, it's ID1 is the point I'm interested in. And then I do a lookup, I do a lookup value of the KMD from this table for that point. So for example, if I'm sitting at A or sitting at B, and I'm looking at my two nearest neighbors are A and C in that case, when I go and say C, I am okay. The point I'm interested in is C, and so now I have to go look up this KMD value for C, and then I have this max where and that should be indented, but to be proper. So I grabbing my MD between which is I'd already the MD between B and C, and then this value that I looked up here, because the distance between this MD value between B and C is 1, but when I look up the distance between the second nearest neighbor for C, it's 2, so this ends up being 2. That's how it works, people. So then I plug that into the formula that they gave me, where I sum up that max MD value and divide it by how many points are in the neighborhood, and then I take the inverse of that. And that gives me these values right here, 0.666, 0.5, 0.666, and 0.333, which, again, when I go here, and we come down here, 0.5, 0.667, 0.333, right? So those are the values that we want. Okay, so we're right on track. All right, so now the last part is the local outlier factor calculation, which again, is that formula that I was talking about before, where I don't know the Hong Kong place, I don't know about that, how they ended up doing that, but regardless, it comes back out and it gives you some examples on how to calculate it. So we get like 0.87, 1.333, 0.87, and 2. All right, so let's go back here and see how that's done. All right, so we grab our KMD, we grab the number of things in our neighborhood, we grab our LRD value for our current row, we grab our ID in the current row. We then do that same filtering, right? We go grab our two nearest neighbors that are out, the 2 points that are in our neighborhood, or at least in this case, it's two, just the number of points in the neighborhood. Okay, so now we get into this crazy thing. So what I'm doing is I'm unioning together ID1 and ID2. Okay. And I want the IDs where that ID is not equal to the current ID I am. So I'm grabbing back just my IDs of the points. Like, for example, if I'm sitting in this B row, I'm grabbing points A and C out of this. So I grab, that's how I get this distinct. So now I know that in my IDs of what I'm interested in A and I'm interested in C. Okay, so then I filter this table by the ID in these IDs, and then I do the calculation that they tell me to do, which is where I'm summing up my LRD values. So for point B, I would be summing up this 0.666 and 0.666, right, for A and C. I divide that by what's in my neighborhood, number of points, which is 2. And then I multiply that by the inverse of my current row's LRD. All right, and so that gives me this 0.875, 1.333, 0.875, and 2, which again, remember, that's what we received here, 0.87, 1.33, 0.87, and 2. Okay, so what does this mean? Okay, well, what it means is that the number that's the biggest number here is the largest outlier. The number that's the second largest is the second largest outlier, et cetera, et cetera, et cetera. So you basically sort these, and the highest value is your most outlier of your data point, and so forth. So it really is up to you to decide what is, and what number is a significant number in terms of your outliers. So it's a bit subjective in that. Is my understanding of the algorithm. So that's how we ended up with these values, 0.875, 1.33, 0.875, and 2. And so then this LOF measure really just combines all of that logic together from all those calculated columns and the tables and stuff, and combines it into one single measure, which goes through and does all of that for you and returns the numbers. So see, easy. This stuff's easy, right? Now, I will go ahead and put this out into the quick measure gallery, just for the heck of it. I haven't put one out there in a while, so now I'll throw it out there. And if you want to download the PBX and really dig into the formulas and that, then knock yourself out. But I mean, again, utility-wise, again, anomaly detection. There is anomaly detection in Power BI, but it's only for line charts, right? So if you want anomaly detection in a different type of visual, that's not going to get you there. Yes, there's R and Python libraries, but those can be a pain to implement, and some places don't allow R and Python. So if you really need to do anomaly detection and you can't use any of those other things, then maybe you find this useful. So anyway, I had a fun time putting this together. It's thunderstorming and raining out, so I mean, I had nothing better to do. So why not do some crazy DAX? All right, that's all I had for this video. Hope you enjoyed it, and I'll talk to you guys next time.